All right, let's dive in. We're about to go on a pretty incredible intellectual journey. We're going to retrace the steps to see how we got from Isaac Newton's idea of gravity as a simple force to Albert Einstein's mind-bending concept of curved spacetime.
You've probably heard this famous quote before. It's elegant, it's profound, and, well, it brings up a really big question, doesn't it?
And that's exactly it. Science isn't just about memorizing the final answer. It's about understanding the process. So today, we're going to follow the exact step-by-step train of thought that took Einstein from one little nagging doubt to a complete revolution in how we see the universe.
So here's our roadmap. We're going to start with the fortress that Newton built, this seemingly perfect theory. Then we'll find the very first crack in its walls, follow Einstein's happiest thought, and see how a tricky problem involving tides forced a complete rethinking of reality itself.
For over 200 years, Isaac Newton's theory of gravity was pretty much the pinnacle of science. It was perfect, it was precise, and it seemed to explain absolutely everything in the cosmos.
I mean, people had been thinking about gravity for thousands of years, but it was Newton, stuck at home during a plague of all things, who just brilliantly connected all the dots, linking what Galileo saw on Earth with what Kepler saw in the heavens, and unified it all into one beautiful theory.
And boy, was his law successful. It explained why planets orbit the way they do, it explained the tides, it even predicted the existence of the planet Neptune using nothing but math. For 200 years, it passed every single test thrown at it. So the real question is, why on earth would anyone ever doubt it?
Well, that first crack in Newton's fortress came from another young physicist, Albert Einstein, during his own year of wonders back in 1905.
Here was the problem. It was a fundamental conflict, a real clash of the titans. Newton's gravity was instantaneous. If the sun just vanished, he said the Earth would instantly fly off into space. But Einstein's brand new theory of special relativity said, no way. Nothing can travel faster than light. That means we shouldn't even know the sun was gone for a good 8 minutes. The two theories just could not both be right.
Now, this contradiction led Einstein to a thought experiment that he would later call the happiest thought of his entire life. And it doesn't start out in space. It starts with the simple feeling of falling.
Think about it like this. When you're in a car and the driver hits the gas, you feel pushed back into your seat, right? That's inertia. But when you're falling, Newton's laws say you're accelerating towards the ground. Yet you feel totally weightless. There's no jolt. And that's because gravity pulls on every single atom in your body at the exact same rate. To Einstein, this perfect balance felt, well, a little too perfect. It was suspicious.
Okay, for every other force out there, the property that feels the force, like electric charge for electricity, is a completely separate thing from an object's inertia, its resistance to being moved. But with gravity, the charge, which we call gravitational mass, just happens to be exactly the same as its inertial mass. Einstein looked at this and thought, that can't be a coincidence, that has to be a clue.
So, Einstein proposed a simple, powerful, and let's be honest, kind of wild explanation for this seemingly perfect coincidence.
He basically said, look, if you can't feel yourself accelerating when you're falling, if you can't even measure it, maybe the simplest answer is the correct one. What if you're not accelerating at all? What if free fall is the most natural, inertial state of motion there is, and it's the ground that's actually accelerating up to meet you?
Now, this is brilliant because it perfectly explains why gravitational and inertial mass are the same, because they are the same thing. What we think of as the force of gravity is just our body's own inertia resisting the ground constantly pushing up on us. In this picture, gravity is an illusion. But this beautiful idea had one massive flaw.
Newton's theory explains this perfectly. If a big asteroid is falling to Earth, the side closer to our planet feels a stronger gravitational pull, and so the whole thing gets stretched out. But in Einstein's new picture, if the asteroid is just floating along inertially with zero forces on it, how in the world could it passably stretch?
This problem of tidal forces stomped Einstein for years. His big breakthrough finally came when he completely reframed the question, not as a problem of physics, but as a problem of geometry. He realized that the physics question, how does a force-free object stretch, was really the exact same as asking this seemingly impossible geometry question. I mean, parallel straight lines are supposed to stay parallel forever, right?
Well, not necessarily. On a flat piece of paper, yes, they do. But think about the lines of longitude on a globe. They all start out parallel to each other at the equator, but as they travel north, they all inevitably smash together at the North Pole.
Why? Because the surface itself is curved. The straightest possible paths on any surface, whether it's flat or curved, have a special name. They're called geodesics. And that single insight from geometry, that was it. That was the final piece of the puzzle. And that single insight from geometry, that was it. That was the final piece of the puzzle. It was the key that unlocked the entire mystery of gravity.
The only way for the front and the back of that falling asteroid to naturally drift apart while they are both following their own straight, inertial paths is if the very fabric of space-time they are traveling through is itself being curved by the mass of the Earth.
So you can see this beautiful three-step deduction. It starts with a suspicious coincidence about mass. It reframes a stubborn physics problem as a geometry question, and it arrives at the only possible conclusion. Mass must curb spacetime.
And that feeling of weight you have right now, that isn't a force pulling you down. That is the surface of the Earth constantly pushing you up, stopping you from following your natural, straight-line path through the curved spacetime our planet has created.
And just like that, by following one simple, nagging question all the way to its logical end, we've rediscovered the very core of general relativity. This was just the beginning for Einstein, of course, the seed of a theory that would eventually give us black holes, gravitational waves, and a completely new understanding of our universe.